So this is joint work with Amol and Milind, Hegde. So the basic premise of this talk will be about how to take the scaling limit of this model of colored ASEP. In fact, more broadly about how to take this scaling limit of ASEP under what's called the basic coupling, kind of a full space-time scaling limit of it. And if there's kind of one message that I want you to take away, it's the idea that in order to extract a scaling limit, you don't necessarily need to have formulas for everything. What you really need to do is you need to find an underlying structure that you can take a scaling limit of, and maybe you can do that in a probabilistic way. So what we'll see is that the Yang-Baxter equation provides you with this link, a sort of hidden underlying structure to this colored ASEP, or colored stochastic six-vertex model, and then using properties of that structure, along with a few formulas, don't get me wrong, we'll take the scaling limit and we'll reveal this universal scaling limit that arises. Okay, so let me start by introducing the model. This is the asymmetric simple exclusion process, and I'll describe it to you in two ways. The first is through what's called the basic coupling, or the graphical construction, and that goes to Liggett and Harris. And then there's also a sort of particle description of it that goes back a little further to McDonald, Gibbs, and Pipkin, and Spitzer. So the basic coupling is very easy to understand. What you do is you start by drawing an environment. And the environment is Poissonian, so it's basically like a white noise. And the idea is that between every column, you have left-going arrows and right-going arrows. They're Poisson, so they occur in independent increments. The left-going arrows are Poisson with rate q, which is strictly less than 1. The right-going arrows with rate 1, so there's kind of more right-going arrows. And everything's independent. And now once you've drawn your environment, the evolution of particles in it becomes deterministic. So if you really want to think about this, this will be a random dynamical system that we're going to introduce. And the way that the particles evolve, the dynamics are that they move forward, so time is the vertical direction. They move along their columns until they encounter an arrow. And if they encounter an arrow, they try to follow the arrow. And the only rule is that if they go to a site that's occupied, that move is not actualized. Okay, so here the first one can kind of pretty easily move to the right. There's nothing to the right of it. But there will be occasions where, for instance, particles will want to move to the right, but they'll be blocked. Okay? So the nice thing about this description is that it allows you to couple together any choice of initial data. Here I've drawn what's called step. Any choice of initial data, and not just at time 0, but at any time to this random environment. Okay. So the question that I'm going to really be asking about is, what is the scaling limit of this picture? Now, at one level, the scaling limit of the environment is just space-time white noise. But think of something like percolation. Right? Percolation is also space-time white noise, but except if you start drawing interfaces, and then you get very interesting scaling limits. And so the analog of that type of interesting functional of the white noise will be the trajectories of the particles, or really the height functions associated to these. So what we'll be interested in is, through the lens of height functions of these types of particle evolutions, what is the scaling limit under some renormalization operation of this entire picture? So that's the sort of premise. Now, maybe this is not the picture you've seen or heard of for ASEP before, and so a more familiar picture is that if you forget about the environment and you just fix a particular initial data and you ask, how do the particles evolve, kind of forgetting about, not seeing the background, then it's according to a very simple Markov process, and the rules are simply that particles jump left at rate q, right at rate 1, and they do so only if it doesn't result in a collision. So here there would be no left-going jump. So this is a continuous time Markov process. Okay, so this is the model. Now, one very nice property, so we want to study the scaling limit of this. And it turns out that studying the scaling limit of this picture, you can do it by actually studying some scaling limits of certain types of fundamental solutions to this random dynamical system. And these fundamental solutions will correspond to kind of starting with these special packed configurations and looking at how these packed configurations kind of jointly evolve. And so in that direction, I want to discuss a special property of this model, which is called attractivity. And this will allow us to reduce the study of this full scaling limit to the study of a colored version of this simple particle process, what's called colored ASEP. So under the basic coupling, it turns out that particles satisfy a property called attractivity. And what attractivity says is that if you imagine starting with two different configurations, so in one case I had 5 particles, and in the other case I remove one of the particles. So I have a kind of a tower of initial datas which are ordered. Then it turns out that under this dynamical system, for any choice of environment, doesn't matter if it's Poisson, the evolutions will stay coupled in such a way as to have at a later time, the solution still satisfy this inequality. So here, when I remove this one particle, you see the deviation actually doesn't move away from where the black particles were, but rather just covers a portion of that. So started ordered initial data stays ordered over time. This is called attractivity. And moreover, if you look jointly at the evolution of these black particles, which we'll think of as kind of the heaviest particles, the red particle, which was this deviation, and then of course the empty sites, this will, if you forget about the background Poisson environment that was driving it, this will itself evolve according to a simple Markov process on colors. And the rule will be that anytime that you have a red followed by a black, they'll swap to black-red at rate q. And anytime you have a black followed by a red, they'll swap to the other at rate 1. So this basic coupling induces, when you look at kind of coupled initial data that are on top of each other, they will induce another, a colored version of the particle process for ASEP. And this is what we call colored ASEP. So of course, when you have initial data that's not on top of each other, this is not the case. But it will still turn out that by studying this special kind of colored ASEP, we can study the whole object in the scaling limit. And I'll explain to you why a little later. So here is the colored ASEP. This is the rainbow version of colored ASEP. And in fact, this is for a specific choice of initial data, which corresponds to coupling together step initial data at every possible location. So the rules of the model are very simple. So, okay, I is always going to be a number less than j. And you associate to every site of z a color, or I'll also associate the colors with numbers. And the rule is that if you have a color j which exceeds color I, they will swap to be ij at rate 1. And if you had ij, then that will swap at rate q to be ji. So it's really a continuous time asymmetric transposition model. Okay, so at every place you do these swaps just depending on the order. So it's a really simple model. This was a game, it's not quite the same, but it's a game I played as a kid. I never solved that. I don't know if you have, but okay, that has bugged me. In any case, we can solve this, so that's good. So this is an example of a move that could occur. So this would happen at rate 1. 1, 0 would swap, and you'd get 0, 1. Okay. So the dynamics of this are clear. Okay, so it's just, okay. So if you had started this actually in a finite volume, let's say that you fixed that there are no particles that can move beyond -3 and 3, but then you can ask what happens over the long time of this model. And in fact, it will converge to a stationary measure. In some sense, this is like the most out of order that things can be, right? Because particles want to be towards the identity, and here you're starting in the opposite. So any guess as to what the stationary measure will be, let's say if you restrict yourself to some finite domain. Now, Jimmy's smiling, he knows these things. No, okay, he doesn't. It's a Mallow's measure. Okay, so this is q to the number of inversions. So the stationary measure is related to these Mallow's measures. But of course, that's in a finite domain. Now, if you're in an infinite domain and you've started with this special kind of, position I has particle minus I, you'll never converge to that. There will still be some sort of local convergence, and you can ask what happens on large scales, and you can ask all sorts of beautiful scaling limit questions. So one that I will not talk about, but we have a paper with Pramit and Amol about this, is what happens to the evolution of the particle 0, or particle 0 and 1 and 2 jointly? How do these particles over a long time behave? And they will end up converging to something that's called the ASEP speed process, a very interesting object. So that's a very local property of this object you can look at scaling limits of. Yep.
So any reason you don't consider the case q equals 1?
We are not considering q equals 1 here, exactly. Now you can certainly consider it. It's very interesting to consider, but we haven't considered that. So that would be like a symmetric case. There's some additional properties that will work. Of course, some of the stuff that we're going to do will break down in that case. So we consider q strictly less than 1. There are interesting questions also about scaling q to 1 and getting different types of objects that will arise there. But yeah, we'll assume q is strictly less than 1. Of course, q equals 0 becomes a totally asymmetric model. And just for normalization from here on out, we will think of time as being scaled in units of 1 minus q. This will kind of put different models on the same page. OK, so the question will be, what is the scaling limit of this colored ASEP? And if you understand that, it will actually end up giving you the scaling limit of this ASEP under basic coupling. One remark. So if you were to look at, say, the evolution of all colors bigger than or equal to 0, so you call these particles and then call these holes, you actually recover step initial data ASEP. And so what's really happening for this choice of initial data is you're coupling together steps at every single location under the basic coupling. That is equivalent to the description of this colored ASEP. OK, so in the study of ASEP, it's very convenient to think of sort of integrated versions of particle configurations. These are called height functions. We've seen some versions of this before. This is the uncolored picture of ASEP. And I just want to briefly describe, because now I'm going to, after this, give you a colored version of this height function. So you imagine that you just had two types of particles, holes and particles. So you could think of the particles as being color 1 and the holes being color 0 in the setup from before. This is equivalent. And you can associate a height function, which what it does is anytime it enters a site with a particle, it goes down by 1. And when it enters a site with a hole, it just goes horizontally. And now, of course, there's some sort of vertical displacement that you need to fix at time 0. You say it's 0 at the origin or something like that. And then the evolution becomes a function of how the particles move. So when a particle jumps, it induces a local move. So here are the sort of, you would add a rhombus. And when a particle jumps the other way around, you would remove a rhombus. And this is just now an evolution on a height function, a local evolution. So studying the scaling limit of this ASEP height function has been hot topic for the last 40 years, going back to 1985 work of Van Buren, Kuttner, and Schwann, who predicted the KPZ exponents, actually before KPZ did, but for this model. Okay, so there are certain scaling that should be associated to this model under which it should have some interesting scaling limits. And then, of course, there's been a plethora of work, first in the totally asymmetric case, and then more recently in the asymmetric case, in understanding the scaling limit of this. And of course, it's also related to the stuff that Daniel was speaking about. So what we're interested in is the colored model. And what is the height function associated to this colored model? So I said that you should think of this as coupled together step initial datas. So we're just going to kind of couple together the notion of what the height function should be for each of those step initial data. And it's a very simple definition. You say that h, x, y, so x and y are integers, t, is going to be the number of particles. So we're starting in this special kind of reversed initial data, what we call packed initial data. So it's the number of particles of color bigger than or equal to x that are to the right of y at time t. So if y is, say, 0, and you ask the number of, or sorry, if x is 0, and now you ask how many particles of color bigger than or equal to 0 at time 0 are to the right of position 3, the answer will be 0, right? So you'll think of all of these as particles, all of these as holes, and so there's no particles to the right of 0 in this case. So the height function will initially take a sort of, well, I can show you what it will look like, in fact. It will linearly increase as you move to the left, and then it will be completely flat as you move far to the right. So the initial data for this 2-parameter height field will have this very simple form of initial data. That's a function of the fact that you have these coupled step initial data. So if I fix for each choice of x, if I look at the height function in y, all I'm seeing is kind of an infinite slope -1 region to the left of the origin, and then 0 to the right of the origin. And now I'm coupling them all together. Okay? So the question is, what happens now as we run the dynamics of the system? Okay, so this is what happens. So we've run it for some long time. Think of t as some long time. And what you see is that this initial kind of step profile, this sharp region, starts to rarefy. And in fact, what you can see, if you fix, let's say you fix x, it's known that there's a hydrodynamic limit to ASEP. There's a, this absolute, well, this sort of sharp transition smooths out to be a parabolic transition on a certain scale. And you're seeing that essentially present in this picture. And of course, this happens for each value of x. But you also see that there are these sort of smaller scale fluctuations around that. And the question becomes, what can you say about these fluctuations? Okay, so what we're going to do is we're going to scale the region that we're looking in terms of the color space, and we're going to scale the region that we're looking in terms of the location, both by t to the 2/3. And then we're going to look at the height function scaled down by t to the 1/3, and we're going to take t to be really large. And we're going to see the following picture. So actually, there's a minus sign to see this picture. So there's some curvature associated with this parabolic shape, and that's what's being represented after putting in a minus sign in this. And this is what this is really showing, is this is the fluctuation field around the hydrodynamic limit as you're varying your color parameter x and your location parameter y in a t to the 2/3 window. Okay? So the question is, what is this thing that you're looking at? And does it have a scaling limit? Okay. Now, of course, there's also questions, why are you using these exponents? So these are these typical KPZ exponents, at least in the case of the scaling of the y parameter, it's very natural. For the x parameter, it takes a little bit more thinking to understand why. So here's the theorem, though. So let me state it. So for any choice of q, we're looking in a time scale that's in units of 1 minus q. And the statement is that this random height function, scaled into this picture, converges to a single scaling limit that doesn't depend on q as I take t to infinity. And this is something that's called the Airy sheet. And this is a two-parameter process in x and y. Okay? So this is a scaling limit as in this topology of these two parameters. And that's what we're seeing in this picture. Okay? Now, there are various things that one gets beyond this. So if you, for instance, fix one of the parameters, say x or fix y, and you look at the process that you get marginally, this becomes this Airy 2 process that Daniel was talking about, minus a parabola. And if you fix both of them and you look at just the 1-point fluctuation, this is the Tracy-Whittam GUE distribution, up to some, again, parabolic shift. And so, of course, this is encapsulating all of those, but more, of course, because it encapsulates the correlation structure between different steps. Step initial data is under this basic coupling, or under this colored ASEP coupling. Okay? It's a universality result because the value of q doesn't matter. So for q is 0.7 and q is 0.2, you get the same limit. Okay? It turns out that also that this is somehow a kernel result, because we'll be able to use this result to prove the full scaling limit of this ASEP under the basic coupling. Now, that's what I'll describe to you in just a little moment. Okay? Any questions about the statement of the result, though? Yeah?
Has the case of q equals 0 been proven before? Or?
No. So even q equals 0 is a new result.
So there's no simplification for q equals 0.
There are simplifications.
Okay.
But and so I'll say a little bit later that there is, in the setting of like last passage percolation, this Airy sheet has come up, but using RSK. But those methods have, to my knowledge, are not applicable, in fact, to prove the TASEP limit, because the TASEP couple, the multi-initial data coupling of TASEP is not the same as the multi-initial data coupling of last passage percolation. Okay, so once you go to this two-parameter object, then last passage percolation and TASEP kind of decouple in some sense. Okay.
So do you get some kind of symmetry between x and y, or rotational symmetry?
Yeah. So in fact, already at the microscopic level, there are these invariance results that Alexei and Vadim and Michael have, and these imply some symmetries there as well. of course, once you go to the continuum limit, then the symmetries are certainly also there. Yeah. Okay, so I want to give you a flavor first as to what this scaling limit is. Now, you've seen it here, but maybe a slightly more familiar description of it I'll give. And then I'll give you some implications of this scaling limit. And then I'll give you the proof, or the ideas of the proof. And this will really boil down to Yang-Baxter and then techniques of what are called Gibbsian line ensembles. So where else does this Airy sheet, or where else should this Airy sheet arise? Well, it should arise as a universal scaling limit of many things, including random two-dimensional metrics. Okay, so the picture, this is taken from a nice paper of De Verne and Virag, is that you imagine you have some sort of deformation of a two-dimensional lattice. Maybe you think of these edge lengths as being random, and you've kind of embedded yourself. And now you're looking from a starting point to an ending point, and you try to either maximize or minimize, let's say maximize the distances that you can get, where you're kind of summing the length along this path. And so, of course, there are many red paths that kind of stay in this directed orientation, and you maximize over all of those. And the question is, what happens to that random number? Random because the lattice is being chosen randomly. So the KPZ theory makes certain predictions. What it says is that if you take your starting point and you vary it transversely in an n to the 2/3 window, and in fact you can allow yourself to vary it in an order n window in this diagonal direction, and you do the same for the end point. So really there's, in some sense, 4 parameters. And then you take n to infinity and you scale this maximal length around some non-universal limit that depends on the nature of the model by a length fluctuation scale of n to the 1/3, then what you get, again, maybe up to some non-universal constant, should be a 4-parameter scaling limit of this random metric, and that's something called the directed landscape. If you just fix if you just allow yourself to vary the starting and the ending point kind of on these two transversals, and you take n to infinity, then you should get the Airy sheet. So the Airy sheet is actually supposed to describe to you kind of from one starting time to another starting time in this scaling limit, what is this metric, this random metric. Now this is not proved. A little while later I'll tell you an example, a very special example where such a thing is proved, but in the generality I'm describing, this is of course completely conjectural. Okay? But it should give you a flavor. And in fact, this notion of what's called the directed landscape is the thing that you get by kind of varying the starting and the ending time. And you see from this metric picture, assuming some independence of the background environment, you see that you should be able to get the kind of full scaling limit of the metric in this 4-parameter sense by composing these Airy sheets between different slices. So if you cook 5 slices and you varied over where you are here and where you are here and where you are here and so on, you get a composition law that will give you the full scaling limit. And that's what the directed landscape is. So what I want to address now is the question of where does this sort of, there is no random metric in ASEP. What we're looking at, this sort of random dynamical system, is not a random variational problem. It's not a random metric. So where do you get this directed landscape object, this 4-parameter family coming up? We already saw that the 2-parameter thing comes from varying the starting location of a step and the ending location where you're measuring the height function. And it turns out that you can, so here's just a reminder, this was our result. But it turns out, and I think I have a video I can show you. There we go. So this is a way to introduce one additional parameter. So we have a 2-parameter thing, but we could also have taken the time parameter to be scaling, right? Rather than just taking time to infinity, you could take it to be like, 0.37 times a large number, or 0.38 times a large number. And that's what's being plotted here, right? This is the dynamics of this height interface over time. Okay? And of course, it will repeat itself. And of course, it's going to, there's a lot of correlation structure as time varies, and you'd like to understand what that looks like as well. And in fact, you can do more than that. So you can study a full 4-parameter object, which is what I said when I said I want to look at this Poisson environment as witnessed through the ASEP evolution, this height function. So this is the object that I was referring to. So you imagine starting with a step initial data at position x at time s. So let's say time s was here, and x is this value. And then I look at some later time t, at how many particles are there to the right of position y. And that's what I call HXSYT. And now I can look at that for different values of S. So let's say this was S1 and now this is S2. And I again run from some different value of X1 my evolution. I haven't drawn it here because I was lazy. But, and I look at the joint law of these height functions over all values of X, Y, and S and T. Okay. And now I define a renormalization operation, which is that I take my time and I'm going to scale it like epsilon to the -1. That was like the n that I had in this previous picture of this variational, this metric. And I scale my x and my y by epsilon to the -2/3. So the kind of location at which I'm putting my step and the location at which I'm measuring is being scaled transversely like epsilon to the -2/3. And then the height function around its centered kind of parabolic shape, I scale by epsilon to the 1/3. And now the scale is that if I apply this renormalization operation to this height field, this 4-parameter field, as epsilon goes to 0, it converges to the directed landscape. Okay? So the entire evolution of all steps over all time converges to a limit, which is identified in terms of these sort of variational problems of this Airy sheet. Okay? So this is not quite a full scaling limit yet, because I can only deal with these special step initial data. So the last step is to get away from the step. And there's one final result that I'll give in this direction, which does exactly that. So what you can do is instead, well, let me go back. So imagine you had some arbitrary initial data now at some arbitrary time, and you apply the same scaling, this R epsilon, to it. What you would like to know is what is that evolution kind of jointly over all choices of initial data and all choices of times at which they're defined and all choices of blah, 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 everything. And in the end, what it boils down to is that the scaling limit of this entire dynamical system is what is given by a variational problem involving the initial data and then the sort of, well, this directed landscape. Here I've written this picture when the initial data is just at time 0, but you can do it at some time s as well. And so this is really the picture that says that even though ASEP does not have a variational representation, in the scaling limit, you recover a variational representation in terms of the initial data in this directed landscape. Okay, so there is somehow poking around in the limit a metric structure. Okay? Now I should say that, so if you look at this for just a single initial data and you look at the law of this object at some fixed time t, then this is exactly what Daniel was talking about, the KPZ fixed point. So they have formulas that describe this object in terms of Fredholm determinants, transition probabilities, and in fact this implies that these formulas also apply in the case of any model that converges to this type of object. Okay. How does one show these results? So these are really corollaries of this special Airy sheet convergence, and the idea boils down to the use of an approximate variational, well, sorry, not an approximate, and a one-sided variational representation that holds for ASEP. So there's a special property of ASEP, which is called height function monotonicity, and it actually gives you a sort of pre-asymptotic inequality that is of a similar flavor. When you pass to the limit, various objects converge, and you recover an equality. So there's a relatively simple argument that once you know this kind of kernel of a result, this 2-parameter convergence, all of the other things that I've said will follow. Okay, the one thing, so I'll give you one more result, and then I'm going to reset and talk about the proof. And this is maybe for Tomohiro and Jan. So Herbert Schwann asked us a question after we first posted the paper, which is whether we could use it to verify what's called the decoupling hypothesis in fluctuating hydrodynamics for this model of colored ASEP. And the answer is yes. So this is a hypothesis about what happens when you start out with kind of coupled initial data of different densities, what happens to the 2-point functions. And indeed, there's a statement that this sort of 2-point function trivializes in all but one direction, and this is exactly verified here. So I won't go into the details of this, but maybe I will say one more thing relevant to this, which is that for these colored models, you can also define colored stationary measures, so kind of multi-species stationary measures. They're complicated. There are descriptions that, for instance, James Martin has for ASEP. Taking scaling limits of those are hard, but in fact, once you have this result that I said, this 2-parameter result, we can actually just, for free, in some sense, take a scaling limit of the joint stationary measures and get this thing called the stationary horizon. So you don't actually need to study the stationary measures themselves. You just need to know that the thing that drives them converges. So in essence, the purpose is to say that once you have these sort of kernel results, this 2-parameter convergence result, you get a lot. Okay? So I'm going to focus the rest of the talk on where does this 2-parameter, this Airy sheet convergence result come from. Okay?
So sorry, but this statement would not apply to AHR model, right?
No. So what we've done is just purely for this 2-color or multicolor ASEP. So this is not a verification for general models, but for a very special model. Okay, so I want to turn and talk about methods. And so you can hit reset and come back awake if I lost you at any point. What I'm going to start by doing is describing a method that was used in this work of Deverne, Othman, and Virag in the context of these random metrics. And this is what I'll call the Airy sheet via RSK. So we've heard of RSK before. I'll talk about this just briefly on this slide. And this will be kind of a model for what doesn't work in the context of ASEP. So ASEP is not a model solvable by RSK. There's a handful of directed last passage percolation and directed polymer models that are solvable by versions of RSK, and this method will work. But for the generality of vertex models, the method that I'll describe is probably the way to go. In particular, works for ASEP and stochastic 6-vertex. So if you recall this picture I described earlier of this random metric space, this is some sort of special version of that. So it's called Brownian last passage percolation. And the environment now is taken to be n independent Brownian motions, or you can think of them as n independent white noises. And the paths that will transverse this are upright paths. So this is kind of similar to this Poissonian last passage percolation Daniel spoke about, except it's a continuum limit. And so what you will do is you'll vary over all choices of upright path, and the length of an upright path will be measured by the increments in this transversal, in this horizontal direction of the Brownian motions along those paths. So for every such path, you have the sum of the first Brownian motion between time 0 and S1, the second one between S1 and S2, and so on and so forth. So the question is, as you vary the starting point by an n to the 2/3 region and the ending point at level n by n to the 2/3, what will be the sort of joint scaling limit of these last passage times? This will be the pre-limiting version of the Airy sheet that we're interested in. So the RSK correspondence actually tells you, regardless of what these driving Brownian motions are, for general functions, it tells you that the push forward of those paths under RSK, which I'm not going to go into detail as to what that is, but it's a path transformation that transforms these paths into non-intersecting paths. If you take Brownian motions as your underlying path for the picture on the left, the push forward is actually Dyson Brownian motion at beta equals 2. So it's an ensemble of n non-intersecting Brownian motions. Now, RSK has these special properties. So Green's theorem says that if you look at the longest path from the bottom left to the top right, it actually is encoded as the top curve of the push forward under RSK. And moreover, if you look at the top 2 curves or 3 curves, there's a kind of a variational problem involving 2 non-intersecting or 3 non-intersecting paths in this Brownian environment, or in the environment on the left. Now, that was generalized by Nomi and Yamada to say that if you start your kind of path not at 0, but at some later time, and you run it to the top, then the variational problem on the left, the value there, is actually achieved by doing the same variational problem, but in the environment given by these push forward under RSK. So actually, I spoke about this the last time I was at IPAM, if anyone remembers. But that was right before the pandemic. OK, so basically, if I'm interested in studying the joint law of varying the starting time by n to the 2/3 and the ending time by n to the 2/3, I need to study the variational problem in this Dyson Brownian motion environment with that same kind of starting location and ending location. And where I'm, now I'm kind of taking my increments and I'm using these Dyson-Brownian motion particles. Now, the nice thing about this Dyson-Brownian motion is that we understand the scaling limit of it. In particular, if you take the scaling limit around the edge in an n to the 2/3, n to the 1/3 window, you convert to something called the Airy line ensemble. So what's the kind of key property here is that the variational problems that you end up getting in this Dyson-Brownian motion, in this Gibbsian line ensemble, they trivialize and only rely on the fluctuations of the boundary, right? So in principle, they're going to rely on everything, but everything over here becomes very dense and very deterministic, and so the fluctuations that you care about in studying this Airy sheet limit only end up being determined by the edge scaling limit. And this is substantiated in the work of De Verne, Arthman, and Virag, and they use this to construct the Airy sheet. So the Airy sheet ends up being constructed as a variational problem in the Airy line ensemble, where you're kind of taking your variational direction in different slopes. So everything gets coupled to this Airy line ensemble. Now the key thing, so everything kind of, all the convergence really happens on the right side. And the key properties of Dyson-Brownian motion that drives this is that it's a determinantal point process, so we can extract finite dimensional distributions, and it's a Gibbsian line ensemble, which says that it's like non-intersecting random walks conditioned at certain starting and ending points. And so from those properties, you can extract the scaling limit of this whole Airy sheet. Okay, so now I stopped. Let me see. Oh, here. Okay. So that gives you this. Okay, so the rest of the talk is basically what happens if you don't have RSK. So RSK gave us one thing. It gave us that this variational problem where you vary the starting and the ending point gets embedded as a variational problem in this line ensemble in Dyson-Brownian motion. And then the determinantal structure in the Gibbs property allowed us to take the scaling limit. So what happens if you don't have either of these? What can you do? And so what will come to save us is the Yang-Baxter equation. And we're going to explain in what way and how this story then builds. So there are going to be,
But it's the same Airy sheet.
you're going to get the same thing, but you won't have, so you won't, well, it's to show that you get the same thing, right? So you won't have these properties for ASEP, right? So ASEP will not have any of these properties, and you want to show that you nevertheless get the same scaling limit. So it's not a matter of constructing the scaling limit, but rather showing that things converge. And of course, the structures that will underlie this will also allow you to prove a lot more stuff about ASEP, so more local fine scale properties. Okay, so it's like, universality of tiling model or whatever. Okay, so here are going to be the key ideas behind the proof. So the first thing is that rather than working with ASEP, we'll work with the stochastic 6-vertex model, the colored one. And this will be useful for us. It will allow us to use the Yang-Baxter equation. And we'll use that following work of Alexei and Amol to embed stochastic 6-vertex into what's called a colored Gibbsian line ensemble, or a special version of the Q-boson, the colored Q-boson model, or colored Hall-Littlewood process. From the description of this line ensemble, there'll be two Gibbs properties. One will be an intercolor Gibbs property, and that will actually yield an approximate version of a variational representation. So this will somehow replace this Nomi-Yamada identity, this RSK property that allows us to kind of embed the pre-limiting sheet in terms of a single line ensemble. And the second one will be the uncolored Gibbs property, which will allow us to extract the scaling limit of the underlying line ensemble in the uncolored model. And so when we combine all of this, we'll end up to be able to prove the Airy sheet limit theorem that we're interested in. Okay, so I'm going to walk you through some of these ideas. So the first is to introduce what this colored stochastic 6-vertex model is. So this goes back many decades. So it's a vertex model, so there are going to be colors that will be indexed by integers. So again, I assume I is less than j. And the rules are that anytime that you have incoming arrows, ij, there's some way that conservative way that the I and j come out, and it depends on the order in which they came in. And the parameters that determine this are q, a quantum parameter, and Z is spectral parameter. So this colored stochastic six-vertex model is stochastic in the sense that if I fix the incoming colors, so I and J, you see there are two vertices that have I and J coming in horizontal and vertical. If I sum the weights, I get 1. And under special choices of Z and Q, or some generic choices, these weights will also be non-negative. So these will actually be transition probabilities for a Markov process that kind of sequentially grows the evolution of these lines. So you should think of specifying some initial data of colors on the left and say on the bottom, and then you sequentially use these weights. You look at, if I had a color 1 and a color 0 coming in, I would see, okay, so this should be a 1 and a 0, and that has probability 1 minus Z over 1 minus QZ of going out and crossing, and the complementary Z1 minus Q over 1 minus QZ of coming out the other way. And so you sequentially build up your evolution of these paths. Okay. And this is a nice picture that Leo gave of what this looks like if you started out with this sort of rainbow, ordered, color 1, 2, 3, 4, 5, 6, 7, so on. You get these very nice stratifications of different colors, and very non-trivial picture here. ASEP, colored ASEP, is actually recovered if I take the parameter Z to 1. So when Z goes to 1, what will happen is that you'll have certain vertices. In fact, these vertices where colors cross through each other, these vertices will go to 0. Weight will go to 0. And so in fact, if you take Z to 1 and you, like 1 minus epsilon, and you speed up time in the sort of diagonal direction by 1 over epsilon, then what you'll see is occasionally, like according to some Poisson rates, you will have these crosses occur. And so if you look in the trajectory of particles along the diagonal direction, then you will actually see that the particles will evolve as colored ASEP. Okay, so there's a very simple scaling limit of this colored stochastic six-vertex, which recovers ASEP. And in fact, you can prove a very strong coupling of colored six-vertex to ASEP. And so what I'll do is I'll actually prove results for colored six-vertex and then transfer them through this coupling to results about colored ASEP. So I'll focus from here on out on this colored six-vertex, and we'll focus, well, on this special initial data, which is going to recover for us this packed initial data for ASEP that we were interested in. Okay. So we want to understand the scaling limit of this, and of course, we need to define some sort of height function and play the same sort of game, but I won't write down explicitly what that height function is, but it's very much in a similar spirit. So colored six-vertex has a very nice property, which is that it's Yang-Baxter solvable. Okay? And it satisfies the Yang-Baxter equation with what's called the colored Q-boson model. In fact, it satisfies an RRR Yang-Baxter equation with itself. But through fusion, you can write down this Q-boson Yang-Baxter equation. Okay? Many of you, I imagine, have seen Yang-Baxter before, but it's a statement of equality of local partition functions. So if you specify the values of incoming arrows kind of on the external, so here these are all the kind of arrow configurations externally. So these vertical directions are going to be bosonic, which means that they can accommodate arbitrary numbers of arrows of arbitrary colors. So these are kind of multi-arrows. And once you've specified these boundary parameters as well as spectral parameters x and y, then the partition function, which is given by the sum over all internal configurations of the weight of the picture of the left and the right, will be the same. Even though the pictures on the left and the right, you've moved this vertical line through the cross. Okay, so this is a nice local property. You can check it. Of course, proving this is easier than coming up with it. And it took a lot of people a lot of time to come up with solutions to this type of Yang-Baxter equation. So I won't go into the details of that, but we're going to work. Now, the weights are not so simple, but maybe the one thing I will say about them is that when Q equals 0, they become zeros and 1. So they become really simple when Q equals 0, and when Q is positive, they're a little bit more complicated. They involve powers of 1 and 1 minus Q and of Q. Okay? So nevertheless, you can do something. Once you have this Yang-Baxter relation, you can prove a relationship between the stochastic six-vertex model. You can embed it into an object that you could call the colored Q boson or the colored Hall-Littlewood process. And this is an argument that in the uncolored case was done by Borodin, Buffetov, and Wheeler, and in the colored case by Aggarwal and Borodin. And the argument goes as follows. So here you have a colored stochastic 6-vertex model with these sort of, well, actually arbitrary initial data on one side. You say specify where the arrows are coming out on the other side. And because over here you have actually a trivial weight, if one looks at the properties of these Q boson weights, the arrows have no choice. They just need to go horizontally. You look at this, you set the spectral parameters here to be 1 and here to be z. And the weight of this entire picture on the right is 1. And the weight of this picture is the probability distribution that for a given initial data stochastic 6-vertex, the outgoing arrows are as specified. So this is an object we care about. This is some statement about stochastic 6-vertex. Now, if you use Yang-Baxter, you can take these local. You see you have a vertical and a cross. So you can start to migrate that to the left. Now, these dot, dot, dots you think of as some large number. You move that through, and then you move the next cross and the next cross and the next. None of this changes the overall partition function specified by the boundary conditions. So the boundary conditions are where these arrows came in and where they go out. And in the end, you have a picture which has the exact same partition function, and it looks, now I've moved this cross to the left. I've moved the vertex model to the left. Now, for finite values of dot, 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 these arrows can kind of make their way up and over arbitrarily. But if you take dot, dot, dot to infinity, then in fact, you see that the arrows need to basically move on the bottom section, and that's because the spectral parameter there is 1, and the spectral parameter here is z, which we're going to assume to be less than 1. And if you ever had an arrow that made its way up kind of infinitely far out to this region, it would need to go horizontal infinitely, and that would come with a factor of z for every horizontal step, and that would penalize you to a penalty of basically 0. So you would get kind of a 0 probability associated to that event. So there's this trivialization that occurs where now you have this trivial weight on the left, and you have this colored Q boson model on the right with the specified initial configuration that has come down here and a specified boundary condition here. And so these paths will kind of make it infinitely far over, and then they'll kind of make their way up last minute in the last few columns. And here there's, of course, kind of an infinite number of configurations, but you see that the weight of the pictures are the same, so you can normalize this because the thing on the left was normalizable. You can normalize this to be a probability distribution. So the measure that you get on these paths over here on the right is what's called the colored Q boson model. And what is very important is that the marginal, the kind of probability of outgoing arrows here matches the probability in this first column of outgoing arrows. So let me restate this in a way that will be convenient for us. So on the left-hand side, we have a probability measure. So there's some normalization I'm not writing, but it's explicitly computable. A probability measure on these infinite configurations of arrows. So here I have just color 1 and color 2 arrows. They come in, they go infinitely far over, and then they make their way up. And I'm actually forcing them to exit at the top. And the statement from the last slide says that if I look at the marginal distribution of this measure on the first column, this is the colored height function of ASEP. So the colored height function of ASEP gets embedded in the first column of this Hall-Littlewood process, of this colored Q boson model. And of course, then there are these other lines. But because this was specified as a vertex model, there is a nice Gibbs property. You know, if I erase some section, I can resample it according to those weights. And in order to realize that Gibbs property nicely, we're going to just do a change of variables and encode this in terms of what are called line ensembles. So here I've kind of, this is one instance under this Q boson, colored Q boson model of such an ensemble. And what I do is I look at the first column, and I'm just going to keep track of how many horizontal arrows are above each level as I move up. And this is going to correspond to the stochastic 6-vertex or through a limit ASEP height function. I can keep track of an uncolored ensemble where I just keep track of zero, you know, how many 1s or 2s there are. And then I can also keep track of how many 2s there are. And if I had more than 2 colors, I could keep track of number of 2s and 3s and number of 3s, or number of 1s through n and number of 2s through n and number of 3s through n. So I get a whole kind of ensemble of these line ensembles. This is the uncolored one. It's purple because blue and red become purple when you mix them. And the height is, so if I look here, there are 4 horizontal arrows above me. So the height of the top curve, which is corresponding to the first column, starts off at 4, and then it stays 4, and then it goes down to 3, and stays at 3, and goes down to 2. So that's what's happening for this top curve. It's kind of making its way down. Eventually, it will be 0, because above height 7, there's nothing. And then I do the same thing for just the blues, just for the 2s, and I get another line ensemble. That's the top curve. And then the second curve, I do the second column and the third column, and so on. So this is just a transformation. Now, it will turn out, so the top curve here is exactly the uncolored, the number of 1s and 2s, 6-vertex height function. The top curve here is just the number of 2s height function. So I want to know how to take a joint scaling limit of like this top curve and this other top curve, or do that kind of for arbitrarily many colors and take joint scaling limits of these objects. So you see already here, I have a more complicated setup than in RSK. In RSK, I had a single line ensemble, and everything was encoded in terms of that. Here, I have kind of, for every color, I have a different line ensemble. But all is not lost. So there is a special property, which is called the intercolor Q-boson-Gibbs property. And I want to describe what that is. So if you remember, when Q equals 0, these Q boson weights, I said there was one thing you should remember, which is that they become 0s and 1s. And what that means, actually, is that if I know my color 1, so my uncolored line ensemble, if I know this, I can actually recover my color 2 line ensemble, just in a deterministic way. So when Q equals 0, this special ASEP case, the second curve of the second line ensemble can be recovered from the the kth curve of the second line ensemble can be recovered from the kth curve of the first and the k plus first curve of the second through a simple variational problem, something called a Pitman transform, something that comes up a lot in RSK as well. So you could, of course, iterate this, and I'll give you what that means in a moment. But what it essentially says is that, let's say I want to know the second curve of this, or the first curve of this second line ensemble, I can get it through a variational problem in the first line ensemble, exactly when Q equals 0. When Q is not equal to 0, it fails. But it doesn't fail by that much. So if you look at the weights and you do some careful analysis, you see that the variational problem is approximately true in some sense that the probability that it varies by more than m from this Pitman transform is small. It behaves like Q to the m squared. And so what this will mean is that as you take a scaling limit of these pictures and you care about fluctuations that are large, that are like capital N to the 1/3, the cost of such a large fluctuation becomes prohibitive. It becomes like Q to the N to the 2/3. So it becomes absurd, and in the limit, you actually recover a variational representation that the second thing is, the limit of the second thing becomes a variational problem in the limit of the first thing. So this RSK variational, Nomi-Yamada identity is not true, but you have some approximate version of it that you can recover, that you can, in the limit, that becomes the actual variational problem. This is what happens if you iterate the variational problem, this Pitman transform. It becomes actually exactly like in the last passage percolation model. You kind of take a soup over, the k plus first curve. Here I'm looking, at the jth curve. I iterate a bunch of times, and I get a variational problem in the increments of the first line ensemble that gives me the second one. So this really, if you kind of take k to infinity, this gives you a way to encode the entire second ensemble in terms of the first when Q equals 0, and otherwise it gives you an approximate way of doing that. So that kind of covers the first part of this picture, this relationship between the line ensemble and the Airy sheet. And so the question becomes, how do we take the scaling limit of the uncolored, this purple line ensemble? And for that, we use the Gibbs property and certain universality result that refers to the Airy line ensemble. And so let me describe to you the Gibbs property of the uncolored Q-boson line ensemble. So this is where you look at the first, colors 1 through n, or colors 1 through 2. And when Q equals 0, if I look at, say, the marginal distribution, I have this ensemble of curves of, say, the second, or a given curve, then actually, given the curve above and below, that will be marginally a Bernoulli, a non-crossing Bernoulli bridge. So when Q equals 0, my Q boson Gibbs property is just that of non-intersecting Bernoulli bridges. It's a very simple object. And we know how to take scaling limits of such things, Brownian watermelons, or these things that Daniel showed pictures of, these PNG line ensembles, using Gibbs property and using the determinantal structure. When Q is positive, you get an additional factor that messes up this Gibbs property, and it becomes very complicated to analyze. And so the real challenge becomes, how do you take a scaling limit of this uncolored Q boson model in the presence of this rather complicated Gibbs property? And well, the premise is the following. You actually can use the Gibbs property, but the Gibbs property fails in a very important way. It lacks the so-called FKG inequality. So the idea becomes that you know that the top curve of your line ensemble has a 1-point Tracy-Whittem fluctuation. It also has this Hall-Littlewood, this special Gibbs property this Q boson Gibbs property I was describing. You would like to show some tightness result under a scaling limit and properties of the limit that will identify you. There's a recent work of Aggarwal and Huang that gives a sort of strong characterization of the Airy line ensemble. And so once you can show tightness of your ensemble at the edge and this Brownian Gibbs property for all limits, then you actually are able to identify the scaling limit. And so the challenge becomes to prove this tightness of the line ensemble at the edge. And really the kind of fundamental problem there is that the Gibbs property fails to satisfy monotonicity, it fails to satisfy this FKG inequality that would say that if you kind of are looking at the marginal law of one curve and you vary the curve below it, you think that as you drop the curve, the law here drops. But actually, the opposite occurs. So there's some fundamental violation of monotonicity that you need to get around. And so it takes quite a lot of work. You end up proving some very weak version of monotonicity and kind of reworking the whole theory of Gibbsian line ensembles. So that gives us the last step. And when you combine all of this, if we put it all together, we have, if we let's say we're interested in two different slices of, we're going to do finite dimensional slices. So you're interested in two different slices of this fluctuation field, this two-parameter field. You can embed that in these two line ensembles, so line ensemble 1 and 2. There's an approximate variational formula that identifies the second one in terms of the first. We care about the top curves. The first one converges to the Airy sheet, and the second one converges, well, through this approximate variational problem to a variational problem to the Airy line ensemble. And the second one converges to a variational problem in it, and that exactly gives us this description of the Airy sheet. Okay, so the underlying convergence of this and the approximate variational problem are the two pieces that become relevant in order to extract this. And of course, if you had multiple slices, you would get a similar sort of embedding of more colors into this picture. Okay, so just to summarize, we had the basic coupling of ASEP, and that gave rise to this colored ASEP. We had a theorem that said that the ASEP sheet, this object, this fluctuation of the height function, converges to the Airy sheet. There are various corollaries. So the ASEP steps under the basic coupling converge to the directed landscape. There was this convergence of the random dynamical system to a variational problem in this directed landscape. There was this decoupling hypothesis. So all of these came from the initial theorem. And that theorem was proved by the Yang-Baxter equation combined with two versions of the Gibbs property. One was the intracolor and one was the uncolored Gibbs property. And your ability to extract the scaling limit relied on this ability to identify the scaling through this strong characterization. Now, of course, the nice thing about this picture is that the methods should be applicable to the whole hierarchy of stochastic vertex models. Here I worked at this colored stochastic 6 vertex model. The RSK stuff kind of works in these models down here, these polymer models. There are, of course, many other models that are not drawn into this picture. And hopefully one can also use these structures to probe other fine details, mixing times, things of this sort. So I think I'll stop here. Thank you.